So, good morning, everybody. First of all, let me thank the organizer for inviting me and giving me the opportunity to present our research. We talk about this strange system, but you will understand it in the following. Let me start by presenting also our collaborators for the experiment Cosmotron for the IFAC in Florence, and for the theory, which has been developed in different aspects, Stefano Lepri and Stefano Lubini, and Antonio Politi and Sergei Yanchuk. So the outline is here. We talk about the configuration, which is this strange named system, the LANER. I will present a simple linear model and we'll try to discuss many of the remarks concerning it. And we'll present some experimental realization and some results, initial results from this system, and at the end I will draw some conclusions. So motivation. Motivation is everything started with the idea of designing a new system, a laboratory-created system about networks using optical fibers and lasers. So the advantages are, of course, the possibility to play with it with a lot of flexibility, reproducibility, great control parameters. Of course, if you are in the lab, you have laser by hand, you are on the system by on your table, so you can play very easily with them. And of course, another important tool that we can use is the fast time scales that you usually have in optical system, which gives you the possibility to perform a very accurate statistical analysis, which are very important in complex systems. So let me start with a small derivation. What is a laser? So a laser is something which is usually well known, but at the very end is based on top of two main ingredients. The first of all is to have an active medium, that is something which is able to give you some coherent amplification of the light coming into the system. And the second important ingredient is to have a cavity, that is something which is providing you a feedback on this signal. So usually you play with two standard configurations, which are the normal, say, laser, which is a kind of linear system. So you have a linear cavity provided by two mirrors here, and then you put some incoherent energy into an active medium, and then you have some feedback coming from the mirrors. And when everything works, you have some coherent pulse emission from this side. And you have the same behavior in the slightly complicated system. You have some traveling wave into this ring configuration, but the behavior is at the end the same. So you have the mirrors, and then at the end, when the light is, say, processed by the active medium together with the feedback from the mirrors, you have some light emission outside the mirrors. So, which is the concept of the LANER? The concept is, we consider an optical network, so something which is possibly very complicated, realized with optical fibers and couplers, and we put into this system some number of active elements which are able to amplify the radiation that we have into the system. So at the very end, you have something which is a network, which could be very complicated in principle, containing possibly many active media. And this system works as a kind of network laser, and we call it LANER, that is laser network. So this is just to show you the possibility that you can have this system. So you may have something which is very complicated. You don't need to have a simple configuration. So a simple configuration are the standard laser configuration, that is linear and ring. Here you have a configuration which is based on a network, which could be, as you know, something very complicated. And moreover, you may have many active medium. So you don't need to rely on just one active medium as in the standard laser, but possibly you can insert many of them. So the main remark is that the LANER is a generalization of the laser, in the sense that the simplest network that you can build with this system is the linear or the ring, which are the standard laser with just one active medium. And that's all. So the laser is simply the simplest possible laner that you can build using this idea. Experimental implementation are, in this sense, quite simple. Why? Because we are just building a network. The links of the network can be done using optical fibers. So you have a lot of flexibility in the configuration, because you can then join different fibers using optical couplers, which are in principle even N by M ports, so you may connect links in many different ways. You have also, since you are just looking to arbitrary complex topology, you can also use different kind of couplers which are typical of optical communication, such as circulators or other stuff, which are easily provided by commercial providers. Concerning optical gain, is up to you. You can have pump Erbium doped fiber amplifiers, which are what we are using, but you may use semiconductor optical amplifiers, some amplifiers, and whatever. Important points. You have very large gain bandwidth. So you are in a situation where the system can display highly multimode dynamics. So you are somehow in a hydrodynamic limit. Let me remark that optical isolators can be also used to select the propagation direction within the links, so you can also play with to forbidden one direction within the network. And okay, you have a system that at some point you need to see what's going on inside, so you put one more or more than one power splitter, and you draw some energy outside the system, and then you put a detector and see what's going on inside. In our system, we use a sample, something which is very simple. So we are just using 2x2 power splitters, 1 or 2 active medium, and a single link sync direction detection, which is simple for our simplest case for our system. So let me split the system in 3 conceptual blocks. So let's say in the center you have, say, a sketch of a possible configuration. So you have a ring here made by a 2x2 splitter, and you have something which is here and another one which is here. Then, of course, the network, the complete network is this stuff here made by also this and this. Then you need to put an optical gain somewhere, and this is done by this block here. So you put some light, then you have an isolator, you sum it with some pump, you go in active fiber, which is providing optical amplification, then you remove the excess pump, and then you put the optical signal, which is now amplified, back into the system. So this is just, say, an amplifier. Okay, could be very complicated, but it's just an amplification from our point of view. And this stuff is, say, the detection block. So you are, again, the network is here, so you put a splitter, you take some power outside the system, and then you have a detector, and then this is converting light to electricity, and then, of course, you play with it. So you can calculate digital scope, signal analyzer, whatever you need for your analysis. So in principle, you may have many of those blocks, in the sense that you may have many systems which are able to amplify your system. You may have more than one detection systems, of course, somewhere. And this block could be even much more complicated than this. Some simple example experimental setups that we have in the lab. So you are just starting with, say, simple ring, which is the ring laser, but it is the simplest possible layer that you can build, but you can do something more complicated. So you can put 2 rings or more than 2, so these are 3. Or you can even play with something which is not simply a sum of rings, but is something which is topologically more complicated than this. And here you have also 2 different amplification blocks. some experimental results. So you can see that increasing the pump power, that is the amplification that you have in your amplification block on the horizontal axis. At some point, this is the power that you get from the system. At some point, you have the typical behavior of a laser, that is you abruptly start to emit a lot of light, and this is the threshold of the laser, which is quite famous in laser physics. And this is very beautiful because you have a network, and sometimes you realize that this could be a very complicated kind of laser, but at the very end, it is in fact a laser. So this is even more complicated because it's the other configuration that we had before, so this one, and in this case, you have the same behavior, so you can see the same kind of stuff coming from this system. Another confirmation is here. You may also measure the, say, oscillations that you observe in the power intensity, and it is expected to have some relaxation oscillation just scaling with the pump that you are putting into the system, and the scale is expected to be here according to this law, and this is very well done with the system. So at the very end, we have a result, so this is the point. Let me start also to depict a small linear theory of the system, which is the simplest theory that you can do. The idea is very simple. Your observer are the field, the electric field that you have in the system. So it is very important to remember that we are dealing with complex quantities. So it is important both to have the amplitude and the phase, because in fact you need to match the phase within the whole network, and this is something which could be very complicated at the end, but it is something that is working. So you describe the propagation of the field within the links by a simple linear propagation theory, and then you make a model for the splitters, and then again here you play with say matrix, because we are just considering unitary scattering matrix S, so you are not losing power in the splitters, and at the same here you are not losing power within for the propagation. Of course, you can then introduce some characterization of the propagation, so you will again consider some losses within the propagation in the normal links, and you will consider some gain in the case you are traveling through an amplification part. So what you find at the very end, you have a linear theory, so you build a matrix, all the propagation coefficients, whatever, and you find that you can write a condition which is something of this kind, so a relation between the propagation part, which is a complicated matrix containing all the propagation parts in the links, and the scattering part containing all the transfer function of the splitters, will combine in a network matrix, which by construction has to emit the eigenvalues equal to 1 for consistency. And this condition, which is this one, that is, we are looking for the eigenvalue equal to 1, is an equation which will allow you to find the solutions, the complex poles of the spectrum of the propagating description, which are nothing less than the spectrum of the network modes of the network. So when we have a situation such that the real part of these eigenvalues are equal to 0, we have the lasing threshold of the network, and the k vectors, or the frequencies at which you have this condition, will have the meaning of the modes we are excited at the threshold of the lasing behavior. So the laser will start to work, emitting some coherent emission for this value here, related to this frequency here. Okay, this is a kind of, say, formal description, but at the very end, it's exactly what you have in the standard laser. And, but we discovered something more, because this is nothing less than the quantum graph formulas that you have in other systems. And this is exactly the same behavior. Of course, in the quantum graph, you have everything concerning losses and gains equal to 1, because you are in quantum realm, so you are not dealing with losses or amplifications. So somehow this is a kind of, again, generalization of the quantum graph description, because you are dealing with amplification and gains instead of just having everything equal to 1. Sorry. Okay, some features. So we are giving a description which is quite simple because we are not introducing any kind of non-linearity that, of course, we have in the optical systems in the amplification blocks. But this is a good description of the cavity, which is, of course, a complicated system because we have to match all the possible boundary conditions for the propagation of the field. Gain and losses are treated in the very same way, so we are just something which is, okay. We will need some extension of the theory, so a full description of the gain value put in some nonlinear treatment. And anyway, linear theory will hold for the rest of the network. So, as I showed you before, everything has to be treated in specific way. Some results. So, okay, just to give you some feeling. Here you have what we expect from theory. So you have many poles, increasing the gain from top to bottom. You take all the real parts moving from the negative to positive values. So you are crossing the zero part. So here you are at the threshold. You start to see some emissions. So you have some lines in the spectrum putting some light at different frequencies. And okay, so here you have some numerical descriptions coming from the linear model, and you have some experimental spectrum coming from the setups that I showed you before. Okay, I will show you some picture just to give some feeling. This configuration, you have different values of the gains increasing from, again, from top to bottom. So you have nothing here, and then you have a lot of peaks. Situation is very complicated because, of course, even if this configuration appears to be very simple, you have a lot of possible frequencies excited in the system. Even more complicated is this configuration. You have two different gains, so you can increase one pump from left to right and another pump from top to bottom, so you have a very complicated spectrum here. So some features which I would like to point out. First of all is we are somehow dealing a system which is a very well, form of description of a network graph theory in a lab. So you have a network, you can build this network very easily. But at the end, you need to use in your mind some mathematical description coming from this network graph theory, because you have something which is strongly ruled by the topology of the connection. So you need to use the methods and the tools coming from this kind of approach. An important point is that you also can connect, as you see with the formula is close to the quantum graph description, to the classical description that you have in the trace formula, which is very useful in the quantum graph approach. Another important point that the system is disordered, so you may think to observe some behavior which is reminding of random laser, and this is indeed something that we have found. We have found some Levy statistics in the description of the behavior of the emission. Other points, phase dynamics is very important because you have variables which are complex and you have to match those variables within the network. So the phase dynamics means that you can think to use the system to perform a level graded simulation of power grids, where the phase dynamics is very important. And finally, this also can be considered as a kind of optical lattices, but a disordered one. So you may think to realize a complex photonics crystals where the possible bands that you can find are mixed in a very complicated way due to the topology that you can build in a strange way according to your desire. So crucial steps, of course, we have to understand better the description of the cavity, because we have to consider the role of topology, all the possible connections that you have in the network, and how this will impact the modes and the behavior that you can expect to have. And of course, you will need to have a good model for the nonlinear part. In principle, you should use the Maxwell block or a spatial temporal equation, but this is very complicated. So we are starting to use a system which is a little more handy. Conclusions. So I present you the LANER, which is a complex active optical network representing the generalization of the laser. Cavity network modes are found using something which is reminding the quantum graphs formalism. You can perform a very easy experiment. The problem is that experiments are simple, results are very complicated. So you need to understand very well how to treat the system. And this is probably the most important message. So you need to find the answers before to give questions. Okay, thank you very much. This is the kind of summary of the what we have in the system.